George Washington, was born on February 22nd, 1732. At least, that's what we're told. However, his family Bible says he was born on February 11th, 1731/2. So, which is it, Mr. I cannot tell a lie? Oh, and don't even ask about 1752. In Russia, 1752 looked pretty normal, but check out what the British Empire was up to that year. Nothing really out of the ordinary, except Ember. The 2nd was followed by the 14th? Were 11 days just deleted? Where'd they go? What happened then? It is time to question time and how the Earth moves. Reconciling both of these things has led to some pretty strange things.
Yeah, where apparently nothing exploded, and that turned into a heap of more nothing, and then that turned into clumps of things, which turned into more clumps of things, which turned into planets and all this sort of stuff, and then eventually us. Okay, yeah, we know all the crazy things. Please, do go on.
We all love time-lapse videos of the stars moving across the sky.
Yes, star trails. Those are one of the first things that made me start to look into the flat Earth. The fact that star trails. I started looking up how fast we're going and whatnot. It's over 1 million miles an hour. And that's not counting the spin, just the rotation of the Earth. So how can we see no movement in the stars, no parallax? You see that just driving down the street. I'll do a demonstration, but I can take a long rod of some sort and point it towards a star. I can take a step to the side and be pointing at a completely different star. And I've moved 1.5 feet. How come I can see the difference moving a foot, but I can't see the difference moving the millions of miles, hundreds of millions of miles from one side of the sun to the other? Or around the galaxy, millions of miles an hour. Maybe he will explain it. Well, I don't think so. They always say that it's because we're too far away, the distances are too large. That's not how it works. If you're standing on the body that's moving, then you notice a lot of movement in the distance body, the body that's far away. But if you're the body that's observing something moving a long way away, you won't notice this movement unless it's a lot of movement. If it's great distances like they say, you won't notice much movement at all. You'll see minor shifts. But if you're the one that's doing the moving, then you will notice a lot of change in shift of objects at different distances. Okay, well, let's see what he has to say and how Vsauce explains it away.
But really, we are the ones who are moving, tumbling through the universe on a giant, wet rock vehicle called Earth with a windshield called the sky. As viewed from above the North Pole, we spin counterclockwise. West chases east. I always remember this by thinking of the US as a weird, mane-headed animal with Texas and Florida legs running forward. But we don't just spin. We also revolve around the sun on a plane tilted 23.4 degrees relative to our spin. It's kind of nauseating at this scale. But from this perspective, you can see that the sun rising and setting is just the Earth pointing you towards and then away from the sun. This motion causes your sunrise, your noon, the moment when the sun is highest in your sky, before your sunset. To more closely investigate this movement, let's talk about meridians. You are on one at this very moment. Your meridian is just a line from where you are right now, straight towards the north and south poles. It's a line of longitude, as opposed to the horizontal lines that lay flat when north or south is up that we call flatitude. Or actually, latitude. The sun is highest in the sky to you, your noon, when your meridian is pointed right at the sun. A cool thing happens at this moment. All shadows around you point directly towards one of Earth's poles, unless you're on the subsolar point. The subsolar point is the point on Earth's surface directly below the sun. It's always somewhere. You can check its current location online, links as always in the description. On the subsolar point, shadows fall straight down so they can easily disappear. Twice a year, the subsolar point crosses over Hawaii, the only place in the US where it hits land. And when it does, it is called Lahaina noon, meaning cruel sun. Straight vertical objects look unnatural during this brief time, like they don't belong, as if they were photoshopped in without regard for reality.
Reality, really. Okay, we'll see if you stick with reality. And so far, sir, you haven't explained anything about the stars. I know you're explaining the movement of the Earth, but can we get to how it pertains to the stars movement? And hopefully you'll explain why we don't see any parallax shift. Okay. Sorry for interrupting.
In Honolulu, a sculpture by Isamu Noguchi called Skygate casts a twisted shadow all day, every day, except during Lahaina noon, when its shadow is a perfect circle. You may not live in a place where the sun ever appears directly overhead, but once every Earth rotation, the subsolar point falls somewhere on your meridian, making it noon for you. The technical name for this noon for you is local apparent solar noon. The clock on your wrist and the clock on your phone don't tell you your local apparent solar time, because long ago we realized that if every meridian had its own time, a person just a few kilometers away, seeing different shadows than you did, would disagree with you on what time it was. So towns adopted their own time. Now later on, this trick was standardized and time zones as we know them today came about.
Okay, so I hear what you're saying, and yeah, I've argued this point too. So you're saying that they changed the calendar because people couldn't measure the time properly. Yeah, that's understandable. Because as you can see here, boat 1, boat 2, and boat 3, well, yeah, they would think the times are different, wouldn't they, if they were using shadows? So I understand why they threw that out, and why you only basically had one timepiece in like the middle of the capital city, or whatever it was. The middle of the capital of the city, I should say. And also, this totally didn't Eratosthenes, didn't he measure the Earth by using the sun's rays? And didn't you already make a video explaining this, Mr. Veritas? Vsauce 3? Yeah, because this sort of blows a few things out of the water. But yeah, I hear what you're saying, and it doesn't mean that the sun's millions, 93 million miles away. But yeah, go on, please, go on.
But that's not all we didn't like about shadow-based sundial time. To explore deeper, we have to begin by asking, what's a day? I mean, obviously it's just the time it takes the Earth to turn around once, right? But according to what? Everything else in space is moving in some way too. The universe doesn't include a convenient sheet of graph paper at absolute rest we can trace paths on. The best we can do on that front is to look at very, very far, far, far away stars. So far away, like distant features of the landscape out the window of a moving car, they barely move as Earth does. Now, to them, a meridian on Earth completes a trip around about once every 23.9 hours. This is called a sidereal day. Sidereal means pertaining to the stars. Even though the sidereal day seems pretty clear, it's not what our calendars and clocks are based on, because there's a nearer star whose position relative to us has a bigger effect on our lives: the sun. Looking down on the North Pole at Earth's counterclockwise spin, the Earth also moves counterclockwise around the sun. After a sidereal day, the Earth has moved a bit along its orbit, so some more rotation is required for the same meridian to point back towards the sun again. This longer definition of one rotation is what the modern calendar and clock is based on. It is called the solar day. But here's the thing. Exactly how long the Earth has to rotate to complete a solar day changes day to day. Our clocks are just based on the average amount of time this takes, so throughout the year, they fall ahead and behind the sun.
Okay, so what you're saying is we do see movement in the stars, and we do see parallax? Is that what you're saying? But it's really, really small? Okay, but we're travelling through space, not just around the sun, so it shouldn't just reset after a full lapse around or whatever, full lap around. And also, so you're saying that it falls in front of 24 hours and behind 24 hours. Okay, so it fluctuates over a whole year, forward and backwards. And this obviously doesn't add up because of leap years, but let's see you explain what it does, because if you're moving through space, if we're traveling through space at over 1 million miles an hour, then what should happen is the parallax should be that stars that are close and stars that are in the background close to those stars, you should either see the space between them, the distance between those two stars, either get closer, so that shorten, or grow. The only time that they wouldn't do that is if they were relatively in line, so above or below so the shift would be left or right of that line. But you would still see the movement, just not as much. Well, actually, no, you would. Yeah, you would see it. You'd see it just the same, I suppose. But you would see it constant. It wouldn't. Does it reset? I don't think it resets. It can't reset if you're constantly moving. But does this explain how we see no movement? No, it tells us we're seeing movement, but we can't see it, and that the day fluctuates over the year. Well, I understand that because days get longer and shorter, but that means that the sun gets up earlier and goes down later, and midday should still be around the same time. Shouldn't it? I don't know that one, but let's move on.
This is a solograph, a picture of the sun's path across the sky every single day. If our clocks actually told us local apparent solar time, if you took a picture of the sky every day at noon, you should get a line of suns. But this is what really happens. Over the course of a year, it will appear as though your clock is running slow, and then fast, and then slow again, and then fast again. This problem was known since at least ancient times, even if its cause wasn't. In order to reconcile the two, the equation of time was constructed. In this sense, equation means to reconcile. The equation of time was applied to what a clock said in order to compute the real time, the solar time a sundial would show. Now, some fancy clocks, called equation clocks, were made that would do this for you, but eventually, we gave up. We gave up and just said, no, the real time isn't what the sun says, it's what our inventions say. Now, this transition was a big one. It was humanity growing up It was like the first time you realize you're stronger than your parents. We realized our timepieces were more regular and turned our backs on the timepieces nature had.
Yep, well, I would agree totally with that last statement. We have turned our back on reality. Yep, totally. But I noticed that chart you had there at the beginning showing, or not a chart, that time-lapse sort of thing of the sun, the sun's trail. I noticed that it comes along quite shallow, and it starts to climb quite quickly, exponential. Is that? That would suffice with a sun moving around the top of a flat surface. And it comes towards us slowly. And it spends more time in a shallow position than it does covering the same distance or the same amount of time in its higher position. Yeah. But turned our back on reality? Yeah, totally. I agree.
But what causes this disagreement in the first place? As it turns out, the answer revolves around revolving, the way the Earth revolves around the sun. If the equator faced the sun all the time and the Earth always orbited at the same speed, the subsolar point would just stay right there on the equator throughout the year, and the amount of extra time spent rotating the Earth needed to do to finish a solar day would always be the same. But those two things aren't the case. First of all, the Earth's orbit is slightly elliptical, so its speed varies throughout the year. When it's moving around the sun faster around the beginning of January, the amount of extra turning time needed to complete the solar day is longer than when it's further away from the sun and moving more slowly. There's more. Because the Earth is tilted, the subsolar point is dragged throughout the year in a circle around Earth that's not the equator, so it changes direction, moving northeast, then leveling out and going southeast, before leveling out and going northeast again. During times of the year when the subsolar point is being dragged by Earth's orbit mostly east, it gains against Earth's spin faster. More time is required for the day to finish. Now, by coincidence, we are alive at a time when both of these phenomena lengthen and shorten days at roughly the same time. So they add up, making September 18th almost a minute shorter than the longest day of the year, December 22nd. For northern hemispherians, December has the shortest periods of daylight, but the whole solar day, from sunrise to sunrise, is for everyone on Earth the longest of the year on December 22nd. People in the north just spend most of it in darkness.
Okay, so it all equals out. But he's saying that it goes faster and slower because of the elliptic orbit. I understand that. But it actually goes faster as it starts to approach, isn't it? As it comes around the side. Because it's being pulled faster and faster, and it gets faster and faster, because it has to be going faster before it gets to the closest point to be able to pass it and then exit, basically. And it won't do that if it's got to speed up before it gets there. It doesn't get there and then speed up and whip around, does it? But that's what he's saying it's doing. And what's this? It's so 12 o'clock is at a different time. So the Earth has to travel further. Well, then 24 hours wouldn't be 24 hours. From sun up to sun up, from sunset to sunset, that's not 24 hours because it changes. And so that period of time isn't 24 hours. It's either forward or behind it, depending on where you are in the season. So that's not right. And that's what you said before. It goes forward and behind the day. We're all seeing the sun at the same point, so I sort of, don't understand what you're saying there. The Earth's spin gets faster and slower. I thought it was just constant. Just So it speeds up and slows down. And we don't notice that change? Oh, come on. We're apparently 99% empty space, and so is all matter, but we can see it all. That just doesn't make sense.
Earth's tilt, it doesn't just affect how long a day is, it also affects how long a year is. This is because the Earth's tilt is what causes the seasons. For the half of the Earth tilted towards the sun, the same amount of solar radiation is spread across less space than it is on the other half, so there's more heat energy laid down per area. This causes what we call summer and winter for the other half. The amount of time from one of these seasonal orientations of the Earth to its occurrence again is called a solar year, or a tropical year. It's a very useful way to define a year because it contains every single season exactly, since it's based on the very orientations that cause them. But the problem is this: the number of solar days that occur in a solar year is not a whole number. It's almost 365. But after that many solar days, about a quarter of a day more happens before the solar year starts again. This makes designing a calendar more like designing a calendar. If your calendar only ever has 365 days in a year, over time, those dates will drift from the seasonal positions they used to occur during. Unless, this extra quarter of a turn adds up to a full day after 4 years. See, March 1st is coming a day too soon now, so if we just delay March by adding an extra day at the end of February every 4 years, a leap day, we're back on track. Leap days do not add days to your life. You're still going to live the same number of them. They just change what we call them. But really, who cares about being 1 day earlier every 4 years? I mean, 1 day isn't much, you'd hardly notice it. But over time, well, if America's founders had declared not only independence from Britain, but also from leap days, and abolished them from happening, today, 240 years later, their calendar would be a full 2 months ahead of Earth's position, putting America's coldest winter days in April and its hottest summer days in October. Adding a day every 4 years is what the famous Julian calendar does. Introduced in 46 BC by Julius Caesar, it was the de facto standardized Western calendar for a very long time, more than a millennium. But it's not perfect. Look closely. Leap days actually move the calendar just slightly too far each time, because I lied. 365 and a quarter solar days don't occur within one solar year. The real number is slightly less and fluctuates year to year based on long-term changes to Earth and the Sun's movements, which means adding 1 day every 4 years is just a teensy-weensy too many.
Okay then, so that doesn't really make sense. The tilt of the Earth, yeah? But the sun's intensity. That doesn't matter really, does it? So that point at the top where the yellow line hits. Okay. So that's why it's all thawed. It's in winter, but it's all thawed. And apparently the bottom part there, yeah, winter. What about that bottom bit down there? Where the South Pole is down there. You can see that. Why is the South Pole not melted? Or why isn't the part where the yellow line there is at the top? Why isn't that? Why isn't that frozen? I don't know. It doesn't make any sense. Doesn't make any sense at all. Should be frozen, and the bottom bit down there should be thawed. Because they're the same distance apart, as you can see there. Really. So They get receiving the same amount of light. So if they're receiving the same amount of light, how can it be frozen? Well, it doesn't really explain that. It's not what he's trying to explain. But anyway, it doesn't make much sense. And if after a year, we've only we don't quite do we do just over a full circle. Yes. And it adds a day. Adds a day every 4 years. Okay, I hear what you're saying. But what about when it's done 1 year? Because surely, as you see here, after 1 year, it's out by a quarter of a day. So the Earth should be facing 90 degrees from where it was last year at the same time. And then after 2 years, facing away from the sun at midday, at the same time, and and then again facing 90 degrees the other way, and then to come around and be facing towards the sun again. That doesn't make sense. Because you can't say that it adds a quarter of a day, yet we're not facing the other way. If it added an extra day every year, and then after 4 years we take a day away or something like that, or 4 days, whatever, that'd work. But yeah, and what, you lied? Of course you lied.
By 1582, Julian calendar dates were 10 days behind the seasons compared to where they used to be. Now that's not bad, 10 days in more than a millennium and a half. But the Catholic Church cared, because they wanted Easter to occur exactly when it used to centuries ago.
Okay, so we have to come to Easter. Well, Easter and anything to do with Christ should not be in the same sentence. For starters, the origin and the customs associated with Easter. Well, the Encyclopedia Britannica comments, there is no indication of the observance of the Easter festival in the New Testament or in the writings of the apostolic fathers. The sanctity of special times was an idea absent from the minds of the first Christians. And that's in 1910 in the 8th volume on page 828, and also in the Catholic Encyclopedia. A great many pagan customs celebrating the return of spring gravitated to Easter. The egg is the emblem of the germinating life of early spring. The rabbit is a pagan symbol and has always been an emblem of fertility. I think most people know that. That was published in 1913, and it was in volume 5 on page 227. And in the book The Two Babylons by Alexander Hyssop, it says, what means the term Easter itself? It is not a Christian name. It bears its Chaldean origin on its very forehead. Easter is nothing else than Aster, one of the titles of Baalists, the Queen of Heaven, whose name is found by Layard on the Assyrian movement is Istar. Such is the history of Easter, the popular observance that still attends the period of its celebration, amplify, confirm the testimony of history as to its Babylonian character. The hot cross buns of Good Friday and the dyed eggs of Pashi or Easter Sunday figured in the Chaldean rites, just as they do now. And you can look in Jeremiah 7:18 for some more on that. And so I thought that was just an interesting fact. A lot of people associate those two dates with Easter and the death and resurrection of Jesus together, and they're not together.
Astronomers at the time realized that if leap days pushed the calendar too far behind the seasons, we would just need to celebrate fewer of them to fix the problem. Specifically, we would need 3 fewer leap days every 4 centuries. The rule they wrote to achieve this stated that every 4 years would continue to be a leap year, except if it was divisible by 100, unless it was also evenly divisible by 400. This removes 3 every 400 years. On October 4th, Pope Gregory XIII introduced this new calendar. It took his name, the Gregorian calendar. He also undid the drift that had occurred since the early days of the Julian and declared on October 4th that tomorrow would be October 15th. October 5th to the 14th never happened in 1582 in countries that listened to the Pope. It took the rest of the world centuries to hop on board. England and its colonies, like the soon-to-be United States of America, adopted the Gregorian in September of 1752, by which point their Julian dates were off from the seasons by 11 days, hence the disappearing of the 3rd through 13th. When adopted, the first of the year was also moved from March to January 1st. This explains why George Washington's birthday has 2 answers. Although more closely hitched to the seasons than the Julian, the Gregorian calendar still isn't perfect. Its difference causes dates to become 1 day off from the seasons every 3,216 years. Other calendars have been proposed, like the one Stand Up Maths calculated that drifts off even more slowly. His video is a great watch, by the way. But enough of all of this. Let's sit back and enjoy Earth's movement without trying to divide it up and name it. As a caveat, keep in mind that Earth's oceans and liquid insides and other celestial bodies are always pulling and tugging and sloshing around, minutely changing Earth's movements. Their effect is measurable, but difficult to notice at big scales and also don't look like much in the short term. Short like the length of a human life.
Yeah, right. Same old story. So you don't notice it because your life's too short, and therefore you won't notice it. You don't have enough time. Yeah, right. But it's measurable. Yeah, everything's doable on paper. Of course it is. It's like you can do the maths to show that the Earth is anything you want. It doesn't mean you live there. Come on. They always say the maths fixes this and the maths fixes that. It just answers. It just answers things. But how many different equations can you come up for different answers? As long as they fit what they're supposed to, then they work. But it's just a hypothesis. It's not a fact, or it's not reality. And it's always in a land far, far away, in a place that time forgot. And it doesn't really explain anything. It gives you something to believe in, but that's it. And it's pretty funny how well, not funny, it's sad, that the church would be the ones to seek to change times. Because like, how far out are we really? Because he's just explained that we're out by days, over a millennium and a half. So how many days? And it's a matter of days, and that's all that matters. Days. How far out are we on our dates when it comes to our history before taking the Gregorian? Like, if they factored it in, but it falls on the same time every year. But that calendar's out, so that can't be exactly the same time. But the Bible says they will seek to change times and laws, and that's exactly what the church has done. And it also says that you will know them by their fruit, and that's what they bear. That's what they, that's what you see coming from them. So there you go. No wonder we're confused.
Looking from above the North Pole, the equator spins counterclockwise at about 1670 kilometers per hour. Relative to the Sun, Earth orbits counterclockwise at 108,000 kilometers per hour, along a path tilted 23.4 degrees to its spin. Within our local neighborhood of stars, our entire solar system is drifting 70,000 kilometers per hour, roughly in the direction of the bright star Vega in the constellation of Lyra. And our solar system is part of a giant galaxy called the Milky Way. On a plane tilted about 60 degrees, approximately like the windshield of a car, looking from above Earth's North Pole, our entire solar system races clockwise around the galactic center at about 792,000 kilometers per hour. Our whole galaxy is also moving through the universe. We know this because when the universe was very young, it was so hot, electrons and protons jumped around, and photons of light scattered constantly. They couldn't travel very far before scattering again, so the universe was opaque. But then, around 380,000 years after the Big Bang, the universe cooled just enough for electrons and protons to form hydrogen. Suddenly, abruptly, photons decoupled from this obstacle course and could travel relatively unencumbered. The universe became transparent to light. And since that moment, those early photons have been propagating through space. Every day, ancient photons that last scattered off this opaque fog at the moment of decoupling, a light day further from where Earth currently is, reach us. They are part of the cosmic microwave background radiation. It is visible in every direction. Microwave because although they used to be more energetic, the universe's expansion has redshifted them. Now, some parts of this radiation are more redshifted than others because of our own movement through the universe. Controlling for the movements we've already talked about, relative to this infinite, cooling baby picture of the universe, the first and oldest detectable light, we are headed, riding along in the Milky Way, in the direction that the constellations of Leo and Virgo are to us, at a speed of 2.1 million kilometers per hour, towards a thing we don't fully understand yet, simply called the Great Attractor.
Okay. We know this, do we? No, we don't. There's no way you can know. No one was around. It's a long time ago. 387,000 years after the Big Bang. Come on, guys. It's a load of lies. And, apparently photons scattered in all directions. An explosion throws things out from the centre in all directions. In a vacuum, that would just happen forever and ever, just keep going. And apparently they slowed down, or whatever, just enough. So now we've got photons slowing down. Okay. So they decide to slow down, and then what? Sped up again. Okay. And the redshift. So you're saying that we work out this 2.1 million miles, you said, an hour, towards this great attractor, or whatever it is, that we don't know anything about, and don't even know anything really. It's just a belief, which is normal for science. And what, you're reading this cosmic radio background, and it's the first and oldest detectable light? Now come on. He just told us before that we can't detect this movement over our lifetime. It takes a long, long time. So we can't detect it over our lifetime. So which scientist put all this together over his lifetime and was able to detect it? And which instrument did we use to detect it over more than one lifetime? And now you're saying that we detected it. I just really can't believe that people haven't caught on. This is just crazy. No one was around. They can't date rocks. They're counting all these millennium and thousands of years and hundreds of thousands of years and whatnot. How are they managing that? Okay? How are they managing that? Come on.
This is how you, on Earth's surface, are moving through the universe aboard spaceship Earth. Okay, now stop. This is roughly 100 years of Earth's movement through space. This path we've traced, from where we began here, is the path you will take through the universe in your lifetime. You didn't buy a ticket for this ride. Your parents signed you up without asking. But nonetheless, it is quite literally the ride of your life.
Okay, so that's how far you're going to travel over your lifetime, and the stars aren't going to change. Look how far that Earth's moving. It's moving. Look how far it's traveling. It's traveled all that distance in your lifetime, and in that whole time, Polaris has been the star that we've been looking at. And you know that we're not, flat, to the sun, because we're on that tilt, that angle. So therefore, you know that we're going around the sun at that angle. So as we're moving along, Polaris should be also moving sideways. It shouldn't be staying there, and we definitely shouldn't have Polaris on the records over. I don't know how far it goes back, but it's been observed as the pole star for a very long time. As long as I know that science says it's moved, but if you actually look into it, there is no records of it moving. There is records of it being there, still being there. They say that the pyramids are apparently the oldest structures on Earth, and they say that they're supposed to be mainstream. A lot of people know that there's also other structures that are apparently older, and doesn't matter. They can't date rocks, so they wouldn't know anyway. But if these things are apparently the oldest structure on Earth is the pyramids, they're aligned to Orion, and apparently they still are. And they do things like, apparently some mimic the Milky Way, and you can, they work like clocks, basically, like calendars and clocks. And that's what they used to do. We used to use the celestial bodies and the sun and the moon to date, to do dating, and to use them for seasons and times. And that's what the Bible says. That's what they're for. They're there to serve. For times, calendar, We've used them for navigation. Now, if you move that far over your lifetime, well, then doesn't that mean that the stars should have moved because just us and our galaxy are moving so fast? We're on the outer edge of one of the arms or something, on the outer edge of the galaxy, and therefore a lot of the stars we see in the sky are either other galaxies or stars that are on a further outside trajectory, outside path or position than we are in the galaxy. But those other apparent galaxies and different nebula and all that sort of stuff that some of those spots are apparently supposed to be, and I don't understand. They are moving around the centre as well, apparently, all together. It's all moving together, but outwards as well. It's travelling outwards from the centre, remember? And so it's moving outwards and around at the same time. But we don't see any change in those stars, even though we're on an arc going around the galaxy, the Milky Way galaxy, and we're on another arc going around the sun. And in your lifetime, you travel a fair distance. Nothing changes. We don't have to change the maps every 100 years. Our maps of the stars, in relation to everything, because you can get old celestron devices, and they line up today. Still. Some of them are thousands of years old, and they line up still. So this is just more, as far as I'm concerned, obvious proof that they don't know what they're talking about. They are making it up, and things that they say, a lot of, is either to discredit God in the Bible, or to change what the Bible says, so that many Christians, as they do, will say, "Oh, the Bible and science line up. They work together." Many do. I've heard it a lot. I used to think it too. I used to say silly things like, "Oh yeah, the Earth can be really old." That's up to God, not up to us. Our job is to use what He's given us, the tools He has given us to use, to observe His creation. And we've chosen to ignore that, make our own, and follow it. Even though it doesn't work, it's out. It needs adjusting all the time. We use it, and we think it's better. It's only better because to those people who use it in this world, in this system. Because when it comes to crops, fish, the seasons matter. The moon matters. You need to know these things to be able to survive in the world. But we've made the system of slavery, servitude, and commerce. It's all about producing something as cheap as possible and selling it as dear as possible. All the way down the line. And there could be a lot of people, a lot of middlemen, before it gets actually to you. But what I don't understand is you pay the top dollar. And every single person on that line who handles the goods before they get to you, and everyone who produces the goods, everyone who mines the materials, every one of those people are an end consumer, just like us. Just like all of us, every one of us. We are all end users. Unless we're someone who produces everything, we have to buy most things. And if everyone's on this system where you buy it cheap and you sell it dear, and that's just the mindset, and it's normal and it's good, then it never works. It'll never work. And it just makes things harder. Those are the things we need to focus on. These things, what they're doing here, is they're making you have something to think of in your mind, so that it's, and it's in everybody. Like, a lot of people can spew out this scientific jargon, this NASA crap. A lot of people can spew it out. Most people know the stuff. You know, I used to think I was smart for knowing all this. But obviously they're not telling us the truth. And they're just making it up. That is the most obvious part of it all. That they just make it up as they go. Like, they make new elements, or they make up strange, mysterious things that they can't see, and you know, you don't know they're there. Or they say that they detected gravity waves from something that happened before, before civilization. And what I think is quite funny is they detected these gravity waves, and apparently they slowly rose, like they were, soft, and then got bigger and bigger and bigger and bigger. And for some reason, this is how they detected them. They detected them getting stronger and stronger and stronger. And well, and that's what it is. And what is it? It's gravitational waves. They're a force that you feel pulling, and it's like magnetism, isn't it? A lot like magnetism. Well, I know that we measure a lot of things using magnets and whatnot. That same, those types of things. And if you think about it, they were most probably detecting CERN. Because CERN, over so many years, since it started firing up, they slowly were raising the intensity, the amount of power, and therefore the strength of those magnets. And those magnets apparently 100,000 times, I'm pretty sure it's 100,000, it might be more, 100,000 times stronger than the Earth's magnetic or gravitation or whatever magnetic field. 100,000 times stronger. And they slowly pump that up. And also, they had that LiDAR or whatever it is, that lying radar detector thing, and it was detecting gravity waves that were slowly rising. It's the same thing. They detected the same thing CERN was doing. That's a bit of a coincidence, isn't it? And I haven't heard anyone talk about it or ask if they made sure that CERN wasn't a factor in their findings, in their readings. And for them to do that, they'd have to know exactly what they're doing, exactly how much power they're using and magnetic force they're using. And CERN, you might think that CERN have it all up there on their website for you to see, but they doctor it. I can promise you that. I've seen a couple of videos where people are following CERN, and they are saying, they're showing there's normal activity happening, just there's no readings on the power output and the magnets and all that sort of thing. It's like they've just turned them sensors off. They've turned the readers off. And yeah, you can look into that if that interests you. But yeah, that's apparently what CERT are like. So I doubt they'd give you the information anyway, give you the exact information. But I haven't heard anything about anyone saying anything about that. But yeah, but you can't trust it. Because like you said, you can't detect it over your lifetime. So literally, you've got to have one scientist studying the same thing the next scientist studies, and he's got to take the other scientist's results and keep going. But how does he know that the scientists who put the notes down? That's something that you've got to put it all together and work it out and come up with your findings. And they have to be spot on, but they're always changing their techniques and changing their instruments. So how do you know? And now they're changing the maths. They're coming up with a whole new maths. We got onto this quantum stuff where everything's possible. And yeah, with maths, everything is possible, but it doesn't make it reality. But anyway, I will leave you all with that, and I hope you've learned something. And yeah, good day to you all, and may God bless you all. And keep asking questions. Don't stop questioning. Listen to what they say. The answers are in what they say, because they lie and they contradict themselves all the time. And if you're listening and you're paying careful attention, you can catch them out. And then you just put it together, and it's not too hard to see that they're lying. Okay, God bless everybody. Bye.
I lied.